All right, welcome to your exam cram session. If you're prepping for a security exam or just need a super fast deep dive on cyber threats, you're in exactly the right place. Today, we're doing a rapid fire review of one of the biggest topics out there, denial of service attacks. Just look at this. This isn't science fiction, it's a real-time map of cyber attacks happening right now all over the world. Every one of those lines is a digital shot being fired. It's a non-stop battlefield out there, and that's precisely why knowing how to defend our digital turf isn't just nice to know, it's absolutely essential. So here's what we're going to do. We are going to hammer through 9 crucial questions pulled straight from a computer security exam review. By the time we're done, you're going to have a rock-solid understanding of these core concepts. Ready? Let's get into it.
First things first, we've got to understand the fundamentals. What is the basic anatomy of a DOS attack? What are they, what do they actually go after, and how do they work?
Okay, question 1 is up. How do we tell the difference between attacks targeting bandwidth, system, or application resources? And this is a super important distinction, because an attacker isn't just vaguely attacking a server. No, they're going after a specific, limited resource. So it all comes down to the goal. A bandwidth attack? That's just brute force. The plan is to completely clog the internet pipe with so much junk traffic that nothing legit can get through. A system resource attack is a bit more clever. It targets the server's brain, its operating system, trying to use up all its ability to manage connections. And then you have application attacks, which are the most surgical. They make a specific program, like a web server, do really hard work over and over until it just gives up. And that whole clogging the pipe idea leads us perfectly into question 2. It's the classic flooding attack. So what exactly is a flooding DOS attack? A flooding attack is pretty much what it sounds like. The entire goal is to just send an unbelievable volume of packets to totally overwhelm the target's network connection. And honestly, it almost doesn't matter what's in the packets. They can be simple pings, UDP packets, TCP packets. It's all about pure, overwhelming volume. Think of it like this. You're trying to empty an entire swimming pool through a tiny garden hose. That hose is going to get overwhelmed fast. Now let's talk about a classic system resource attack. This one isn't about raw volume, it's about being clever and exploiting a basic process of how the internet works. So let's dig into the TCP SYN flood. So here's the dirty trick. When you connect to a server, there's a 3-way handshake. You send a SYN, the server sends a SYN-ACK back, and you reply with a final ACK to seal the deal. Simple, right? Well, in a SYN flood, the attacker sends a storm of those first SYN requests, but then never sends the final ACK. The server is just left hanging with all these half-open connections, and that fills up its entire connection table. Pretty soon, there's no room left for you or any other real user to get in. Okay, so now we get the basic moves. For part 2, let's look at how attackers really scale things up, taking a simple DOS and turning it into a massive, distributed denial of service, or DDoS attack. To make an attack huge, and more importantly, to hide where it's coming from, attackers use a core technique: IP source address spoofing. So how does this digital forgery actually work, and why is it so critical? The deception is actually pretty simple, but it's incredibly effective. The attacker sends out a packet, but they lie about where it came from. Instead of putting their own IP address in the from field, they put the victim's address. This does 2 things. 1, it makes the attacker almost impossible to trace. And 2, and this is the crucial part for reflection attacks, any server that gets this fake packet will send its reply directly to the victim, not the attacker. This is one of those foundational questions you just have to get right. What really is the difference between a denial of service and a distributed denial of service attack? It really boils down to 2 things: scale and source. A DOS attack is one-on-one. You have one attacker and one target. But a DDoS attack? That's a mob. The attacker takes control of a whole army of hacked computers, we call that a botnet, and orders them all to attack the target at the exact same time. It's the difference between one person blocking a doorway and a 1,000-person mob trying to crash through it. Okay, question 7 is about a really subtle and clever attack method that doesn't even need to infect computers with malware. We're talking about puppet nets. What are the pros and cons? Puppet nets are pretty wild. An attacker slips some malicious code into a popular website. When you visit that site, your web browser, totally without you knowing, starts sending requests to the attacker's target. Now, for the attacker, this is awesome. It's super cheap, And all the puppets, that's your browser, are completely legitimate, uninfected machines, which makes the attack really stealthy. The big downside for them, though, is a total lack of control. They can't really time the attack, and their army of puppets just comes and goes as people browse the internet.
All right, let's move into our final section. Now that we've seen how these attacks get scaled up, let's talk about the advanced techniques and, more importantly, how we defend against them. Okay, question 6 covers an advanced technique. We've talked about reflection, right? Where a response gets sent to the victim. Well, attackers can crank up the volume on that with something called amplification. Think of amplification as a force multiplier. It's a special kind of reflection attack, but the goal is very specific. Make the reply way, way bigger than the initial request. The attacker finds some internet protocol where a tiny little question generates a massive answer. Then they spoof the victim's IP address, and just like that, they've turned all these third-party servers into unwitting weapons that are magnifying their attack power like crazy. All right, enough with the offense. Let's talk defense. When you have these massive, amplified attacks coming at you, how does anyone stay online? Question 8 gets right to it, asking about one of the main defenses, the Content Delivery Network, or CDN. This is why CDNs are such a game changer. Instead of having just one server trying to take the full force of a flood, a CDN spreads your website's content across a giant global network of servers. So when a DDoS attack hits, it doesn't slam into one single point. It gets absorbed and spread out across that entire network, kind of like a giant sponge. No one server gets knocked out, and for most people, the website just stays online. It's literally defense through distribution. And that brings us to our final question, number 9. This is the one that really ties everything together: the spoofing, the reflection, the distribution, and that amplification we just talked about. So how does a DNS amplification DDoS attack actually work? Okay, let's walk through it. The attacker uses their botnet to send a bunch of small DNS lookup requests to public DNS servers all over the internet. But they've spoofed the source IP address on all those requests to be the victim's address. Now, these DNS servers, they're just trying to be helpful, so they send back an answer. But here's the kicker. The DNS protocol can be tricked into sending an answer that's way, way bigger than the question was. So all these huge, amplified answers get sent directly to the victim, who suddenly finds themselves buried under a mountain of data they never asked for. And you can see it right here. It's a perfect storm. All those little requests from the botnet go out, and these huge, amplified responses all come crashing down on the victim. Ultimately, the whole fight against denial of service is this constant cat-and-mouse game of overwhelming force versus distributed resilience. And that really leaves us with one last thought to chew on. As everything in our lives gets connected to the internet, our cars, our smart homes, even our coffee makers, what does the future of these kinds of attacks even look like?